Yeah. Okay, so yeah, welcome to the second edition of our GReTA seminar. So we're very lucky today to have Jakob and Daniel presenting. But before I introduce them, let me just say briefly that during the presentations, we expect everyone to be muted. You can ask questions in the Zoom chat. We will monitor them and then decide whether we post them to the speaker in order to answer them directly or potentially reply to them in the chat itself. And any questions that can wait until the end, I mean, you're still free to post them, but we may only come back to them at the end of the presentations. Okay, so just to understand how it works, but feel free to post any questions in the chat. So that doesn't disturb anyone. Yeah, we deal with that as we think is appropriate. So our presentations today is basically split in two parts. So Jakob Andersen is associate professor in the University of Southern Denmark, if I understand that correctly. I don't actually know where that is, to be honest, apart from Southern Denmark. So maybe you can say that in a moment. And he's an expert in graph algorithms and graph transformation algorithms and graph transformation tools with applications to chemistry, but also in a more general sense, and an active creator of all sorts of tools implementing these things. So he will start and he will give an overview of the underlying formalism and the tool support. And then Daniel Merkle is a professor at the same university who's been around the block, as I see in his CV, in various different places, including at Harvard and in Vienna and in Leipzig, and has links to lots of other places as well. And he's an expert in basically application of these techniques and other things to chemistry. So and leads a sort of chemical informatics group, which is busy doing these things. So you take the second part and then talk about the applications side of things to chemistry. So yeah, so that's all I wanted to say. So over to you, Jakob.
Yeah, thank you. So so maybe I'll just start with the question about where the University of Southern Denmark is. So actually split in multiple areas in southern Denmark, but the main campus where Daniel and I are located, at least when we are not in lockdown, that's in Odense, in the middle of Denmark, the birthplace of Hans Christian Andersen, if people know him. Yeah, so thank you for the introduction, and yeah, we'll split it into these two parts. So we are maybe a bit atypical in this community, in the sense that we are not really as such in the core of graph transformation, but we are kind of in the middle of just trying to bend the formalisms a bit and trying to bend the reality of chemistry a bit and figuring something out in the middle and making stuff work. And yeah, as Reiko said, in the first half, I'll try to give an overview of our graph transformation system for chemistry. It's one ingredient among many that we use, but it's a quite fundamental one. And then in the last half, Daniel will show some higher level applications of this, what graph transformation actually enables us to do. So if I can get this window to work. Yes. So actually the core of this, the basic model, is really, really old. So back in the day, in the 1800s, Sylvester invented the word graph really in the connection of modeling chemistry. So it's essentially that basic idea that we start with, that a molecule is a simple connected labeled graph. So it's we use the vertex labels to encode both the atom type and the charge as one big entity. And then on the edges, we have a bond type. So even though that chemists might visualize a molecule like this, in the model, it's more like this right-hand side here of having an underlying data structure like this. So why do we have simple graphs? Well, even though we have these double bonds here, that we could have chosen to make those as two parallel edges instead. But semantically, that won't go well because the chemistry, how molecules behave, in that case, two single bonds in parallel, a single bond and a double bond, they behave differently. So it's good to merge them into a new entity. Similarly, well, if we have a molecule, we assume that all interactions with among atoms are encoded as edges in some way. That becomes quite important for some of the next ideas. So the way we get graph transformation into the picture is that, well, we can really just see a reaction as a graph transformation. We'll get to the rule in a second. When we have this transformation, we would like to stay in chemistry world, so we shouldn't change the underlying element type of atoms. We shouldn't. It would be nice to convert lead to gold, but it would be good to not do that. But really, it's not a constraint that we have in the system. It's just something that one should be aware of when we model it. So we use double pushout formalism for transformation. It has some nice semantics for what we're doing, and we restrict all the morphisms to be monomorphisms because, well, if we didn't do that, then we need to have the semantics of how to merge atoms into one. And again, let's not go into fusion physics. So in this way, we have a rule, a left-hand side, a context graph for the rule, and a right-hand side. We have the usual thing. We find a match morphism into a bunch of molecules here, and then we can make a direct derivation. We do allow label changes, both we need it for the edges. Here in this example, we don't have it, but for the vertices, we also need to be able to change labels such that we can change, for example, an O minus into an O, for example. The restriction to simple graphs present us with a bit of a problem in a formal sense. Because what if now we have such a pushout here, where we have the base object being just two vertices, and in both of these sides we add an edge. The pushout object, well, we have in some sense three choices. We could create parallel edges, but we don't allow that. Another way of solving it would be to merge these edges in the pushout object. People have done that in different contexts, but that doesn't really make sense. An edge in our chemical context is really a physical entity. A single bond is a pair of electrons. So merging these two, it would not be the correct semantics. The rule should not have the side effect of creating, say, a double bond suddenly. So our only choice is really to reject this case, that we cannot have this pushout in whatever way. So one way of looking at it is that, well, the pushout is not defined. So whatever algorithm we are running at the moment must abort somehow. There's no defined result. If we connect a bit to the literature, then a more clean way, in a sense, to view it is that we implicitly have on every single rule for every pair of vertices in the left-hand side that are not connected, and where an edge is created in the right-hand side, there we implicitly have an application condition that rules out that there should be an edge already. So this is an example where that condition would then fail, because here in G we have an edge. So here in the result we should have two edges. But this is not something we have explicitly in the objects. This is something we have encoded directly in the algorithms that we simply abort every time we would otherwise create parallel edges. A core part of the graph transformation here is that we are not really transforming graphs as such. We are transforming multisets of graphs. We're assuming that all interactions are encoded as edges in some way. So what we see here on the left-hand side in G is really we have one molecule here, formaldehyde, and then we have this other molecule here, enolized glycolaldehyde it is. And these two molecules are really separate. So we're really transforming here a multiset of graphs into another multiset. Here, it just happens to be that this multiset is the trivial one with just one graph. So what we really do is that we fluently go between viewing a graph as one object here for the transformation and then viewing it as a multiset of its connected components. This also leads to another interesting thing, which is that if we have a direct derivation here, there's nothing to hinder that we just add another graph to the multisets on both sides. But we would like to focus only on what we call proper derivations. So the match morphism should hit all of the connected components. So all the molecules should participate in the reaction. Otherwise, we can trivially add more graphs. That doesn't give us any more chemical reasoning as such. When we then go to the algorithmics of this, where do we use graph transformation? Actually, it turns out that in general, we only have 3 different questions, low-level questions in a sense. The 2 simple ones is that, well, we're given a multiset of graphs and some rule, and now we want to enumerate proper derivations from that, either where we strictly need to use all of these, or we only need to use a sub-multiset of those graphs. So Daniel will speak about an example with enzymatic reactions where this is used heavily. The thing we have worked a lot on is actually where we just have a set of graphs and some rule, and now we just want to know which proper derivations can we make from this set of graphs where we allow duplication of these graphs. So really an enumeration of the language of a graph, of this graph grammar that we can get from it. So this is where we could define a chemistry. So people talk about, well, there's sugar chemistry or there's prebiotic chemistry or whatever chemistry. We could just encapsulate that as say, well, we have a graph grammar where we have an initial set of molecules and then a bunch of reaction rules. And now we exactly want to enumerate which enumerate molecules that we can reach by proper derivations, repeated application of the rules. And we want to get a handle on these direct derivations. So that leads us to that, well, we can really set up this network that we get as a result as a directed multi-hypergraph, a reaction network. And then we can begin to do analysis of this. And Daniel will show a couple of examples of that. And we can generate relatively large ones, but it requires a bit more detail in the algorithmics of how to do that. A brute force way to do this is, well, as an ingredient, let's just take a set of graphs and then this rule, and well, how do we enumerate all the proper derivations? Well, we could just enumerate all multisets of U. Of course, there's no point in enumerating more multisets of cardinality larger than the number of connected components in L. But we could do that and then just try to apply, and for each application that's successful, we take the result H, reinterpret it as multiset of graphs again, and then we can extend our known universe of graphs with these new graphs. It turns out this is actually relatively slow because there's a lot of graphs that will not be matched by every rule. Of course, here we will have a set of rules in general. Another note, which is, well, in this small operation here, that actually hides the fact that we need to do graph isomorphism here to keep track of all the unique molecules that we have. That takes quite a lot of time. But it's worth noting here that the specific case we have here is not just we have 2 graphs, we want to check whether or not they're isomorphic. We already have a known set of graphs, and now we come with one graph at a time, in a sense. I want to check if we have it already. So at some point we recursed into graph canonization and tried to use that for this case. It turned out that the existing tools were not really generic enough for integrating them. So we did our own thing, and you can read more about that in this publication and at this link where you can download the library as well. So instead of enumerating all these multisets, we can use this fact that we really focus on the connected components, both of the left-hand side of the rule and then of these graphs individually. So just as a quick side note before we get to re-implementing this in a different way, if we just take two rules and see how do they relate, well, if we have the left-hand side of some rule, P2 here, the left-hand side, what if now that is a subgraph of the right-hand side of another rule? Well, we should be able to compose these rules and then get a new overall rule. So this is quite natural to do also in chemistry. You can have a pathway that really is multiple steps, and then we would like to compose such a pathway into one big step. So here's an example where we have this embedding of the complete left-hand side, and we get a resulting rule. But if we now look at the connected components of the left-hand side, we could also imagine that we just take a subset of the connected components and embed them, and we do such a partial composition. So it could be this connected component is mapped to this molecule, and this connected component is later mapped to something else. In general, rule composition we can do by, in some sense, exploiting the diagram for the concurrency theorem. We have our two rules, and now we make a common overlap D between these rules, and then following the steps of this diagram, creating pushouts, pushout complements, and so on, we can now get one overall rule here for this composition. The question is, well, these overlaps, how do we select them? And we would like to do something with these overlaps which is related to the component-wise nature of our system. So in the software, we actually implemented several enumeration algorithms for these overlaps. One of them being that, well, let's just try to split the connection components up into two parts and then take one part and embed it, and then let the other one be free, and we can now do these compositions. So there's an embedded language in our Python bindings for the library for playing around with these compositions.
Sorry, Jakob, there are a couple of interesting questions on the chat on essentially motivations for some of the design choices some of the more basic design choices you made, which are probably worth addressing. So
yeah, so Ian's question about why distinguish between a graph and a multiset of connected components. The idea is here, for example, that in this small reaction network, we have this molecule here. In one instance, it acts as a graph alone and can get transformed into this other graph over here. But in another instance, this graph is merged with the formaldehyde up here to form one big graph, which is then transformed into this product molecule. So that means that depending on the context, we will need to do all combinations of combining the connected graphs with each other into multisets in order to enumerate all the chemical reactions. I hope that answers it. Yeah, exactly. It's as Stefan relates. It's really that the molecule entity is really important, and they can recombine. You can imagine that in some fluid in water, you have molecules floating around individually. They happen to bump into each other, and then they react. So, and then after they react, if they now result in two molecules, they will float away again. They will not stay together. So we need to do this recombination into multisets all the time. We are enumerating networks, we're not simulating them in this context here. But this is why that we go into all this connected component stuff. Right. So the trick to speed up the previous algorithm is that, well, once we have a graph, there are three interesting rules that we can rate, basic rules. We can create an identity rule for a graph. We can create a rule that creates a graph from nothing, and another one that destroys a graph. But if we just take this rule that we call the bind rule, then we can really reinterpret a full composition, a transformation as a full composition. We go from nothing into G and then compose it with some left-hand side that we have fully embedded into G. And then for the connected component, well, if we just take a subset of connected components and then map that into G here, then we can perform if those of you that are familiar with Haskell and functional programming, where you can do currying or partial function application, I like to think of this partial composition with these bind rules as a type of currying in graph transformation. So if we now do repeated currying, well, then we can perform full compositions. So in this manner, we can take graphs, and if they cannot have any components embedded in them, we stop early instead of begin to enumerate multisets with such graphs. This means we can do these enumerations quite quickly. We do not require that the disconnected parts are mapped to different connected components. We can have that two connected components are embedded into the same molecule, as long as it's done injectively. So I bet many of you have had a bit of chemistry at some point, and then you were taught that, well, atoms cannot have too many bonds. Hydrogens can have at most one bond. Nitrogen can have 3, oxygen 2. So oxygen, it could either be a double bond to a carbon, for example, or as in water, it could be these 2 bonds, and so on. With carbon can have 4. And this is what we call valence constraints in chemistry. And most of chemistry, yes, this kind of setup is enough, but there's a significant part of chemistry which does not adhere to such constraints. It gets quite complicated. And again, we need to think of bonds. Well, it is pair of electrons. 3 of the cases where this does not go well is that there's a concept of aromaticity, delocalized electrons. Metal chemistry gets really funky. There's also the case that often we would like to do modeling in a sense where we say, we don't want to model all the molecules. We just want to have some part of the molecule abstracted away, and then we have the interesting part as explicit atoms. So we want to have a lot of flexibility in the modeling. So without having to resort to the full stereochemistry that I will briefly sketch later, we can just pragmatically say, well, by induction, if the initial graphs are proper in whatever way the chemist sees fit, and the model also ensures that whatever valence constraints they like are preserved in the rules, then because we have used double pushout, it has no side effects, then by induction, all the generated graphs will be fine. And when we reduce it to composition, well, we only do full and partial compositions anyway to implement transformation. So, and there we embed a component either fully or not at all, so we don't have these overlaps where we suddenly can generate larger valences than we had initially. So this is the basic system, but it's for modeling power. It's quite nice to go further than this. So for example, once you have a molecule, sometimes it's nice to just say, well, actually, I have a double bond to something, or I have a single bond to something, but I don't know what that something is, or I don't care. So we would like to have wildcard labels. Sometimes it would also be nice to just say, well, actually, I want to match a carbon, but I don't care about its charge. So what we implemented was that, well, how about we reinterpret the labels as first order terms using some specific syntax. So if you're familiar with Prolog, this might look interesting or familiar. So here, for example, we could just introduce some type for a tuple and say, well, the first entry is the atom type, and the second entry is here 0 for the charge. Or we could have a variable here signified by having an underscore in the beginning, or we could have an unnamed variable star in the system. So in this manner, we could now specify in a rule, for example, hey, I want to match an atom of type C with whatever charge. This means that now we need to go to a different category for the underlying objects, and morphisms need to change. They are no longer just a normal graph morphism, but we need to now, every time we have a graph morphism, we have mapped labels to each other. That induces a question for unification, syntactic unification. The unification will result in some variable assignment induced originally by the graph morphism, and that is our full morphism, the graph morphism plus this variable assignment. we need to have the distinguished set of morphisms for our rules, where we say, well, we can have just an isomorphism on the variables, and that's enough for having these distinguished morphisms that we need to do push-outs on. Really, this is not something we invented as such. So there's a nice appendix in the fundamentals of oops, I forgot an S there in the book that it goes into this as well. But we really want to solve this stereochemistry problem with the valences in some way. So what we've been working on, is still work in progress to get the full model, is to really go into what is not the full 3D embedding of molecules into space, but just a bit of the local geometry. So if you go to a chemist and ask about stereoisomers, they might explain something like this diagram that I found on Wikipedia. And really this diagram, it's not so formal, because when they say something is isomers, they really speak about which morphisms exist between the molecules. So to make this more formal, well, how can we encode this local geometry on our graphs? It turns out that we can really go down. There's this nice Vesper theory here. And the idea is really, well, a bond is a pair of electrons or multiple pairs of electrons. And each atom core, well, it's a bunch of protons. So it really is just magnetic repulsion. So there is, when you have 3 bonds around an atom, well, they want to arrange in a certain manner. And using that theory, we can define these shapes and some neighborhoods. We want this to be an extension of our model, such we can disable, and we want to have partial information. So we presented this as ICCT a couple of years ago. I think time is running for me, so I'll go through this very, very briefly. The idea is we have a shape category, so with some kind of variable shape, such that we can still have this generalized stereochemistry. And then we have these neighbor lists that then figure out how we are embedded into this local geometry. And then for these geometries, we need to figure out which combinations or which permutations of the neighbor lists are equivalent. So here with colors, we see there are 2 different configurations of the neighbors. Each of them have 12 equivalent permutations. And these permutations, we need to figure out when a stereomorphism is then valid. So for example, if we here have 2 graphs and we map them to each other, we have found an adjective graph morphism where U is mapped to V and the neighbors are mapped like the red edges. Then we have the neighbor lists. Using these neighbor lists, the indices, we can now induce an index map where we really map the position of each neighbor in the neighbor list to the position in the other neighbor list. Now we get a permutation. That permutation we check against this symmetry group that we had here previously. In this case, it turns out this permutation is not valid. This would actually move this molecule into a different stereoisomer. So this would not be a valid stereomorphism. So as an example, we can then begin to have rules with this where we can have the generalized one. We can match a general tetrahedral, map it down to a specific one, and then erase it and then generalize the configuration of this on this atom. There are many interesting ways we can use this. But as a final overview of this, well, it turns out then, well, we have either simple labels or we have these first order term labels, and then we either have no stereo information or we have stereo information. So all these 4 combinations, well, that results in a category that we can work in, and all the algorithms can be parameterized to, well, now you should work in this category. So the basic ingredients of morphism enumeration and rule, mono and isomorphism, and rule composition and graph isomorphism, we need to have variants for each of these. And one interesting thing that we're working on is exactly, well, how can we do canonicalization of graph objects when we have these more complex labels? Right. So with that, I'll give the word to Daniel. I think I should stop share now, and then he can share, hopefully.
Yeah, so does it work? Seems so. So let me maybe present some applications of things that Jakob showed now, not only applications, but just to kind of now take a step back, right? So maybe dragging you even further away from the core of what you are usually doing. And just, I mean, if you analyze chemical systems, there's of course a lot of methodology out there. And some of you might heard of something that is called flux balance analysis, which is very successful to a certain degree in analyzing metabolic networks. I call it here now not accurate, and I will enlighten what I mean by that in a second. So that's one side of modeling where actually entities are not described on an atomic detailed level. On the other side, if you go closer and closer to physics, then you come to molecular quantum mechanics, for example, which is super accurate because you do three-dimensional embeddings of molecules and you compute electron densities over a very small amount of times. It's super accurate, but very expensive. So we try to somehow have something in between where we are as close as possible to the accuracy of QM, and we also interact with QM, but we are more accurate than methods like flux balance analysis, because as you saw already, our molecules, the atoms have identity, and we will exploit this, right? We will exploit this. Why? Because I mean, because we can. That's the first reason. And the second is, I mean, if you look at technologies that are out there, like computing mass spectroscopy spectra or NMR technology, this is from an engineering perspective just mind blowing what you can do in the wet lab and analyze to try to enlighten the structure of a molecule with these methods. But the so to say rigorous or close to rigorous approaches to expand large chemical spaces while keeping the identity of the atoms are not that many out there, right? So that's why that's our core thing. What we do, right? We use graph transformation and all kind of other techniques in order to expand chemical spaces. So here a relatively small one shown on the right hand side. And then we try to use these chemical spaces, which are formally hypergraphs, see them as an over approximation of what could happen, and then try to find motives in there or use this as a design space. So that's what I just want to make clear as the kind of a start, and we'll show examples for that. So the graph transformation you can apply to different modeling levels, so to say. So here on the top right, I have a super simple graph transformation rule, which basically takes a negative charged carbon and a positive charged carbon and then forms a bond. And you might easily imagine that if you apply this rule to some molecules, this will combinatorially explode like hell. So you need to somehow connect to chemophysical properties, like here, for example, I show just as an illustration partial charges, right? So if an atom is very negatively charged and another atom is very positively charged, then they try to attack each other. So in chemistry, you might have seen such so-called arrow pushing diagrams, which are kind of how chemists explain how chemical reactions happen, right? That's a very low level. So the lowest level where we go to, so we don't go to the 3D embedding directly, right? So on the other side, then there are well, I mean, if you just burn burn sugar molecules, right, then they somehow interact, but it's not that they that you want to model this really via individual edge breaking in chemical world, but you have a more rule like Jakob already showed that you can then apply to a set of molecules. Well, then you can go up to crazy levels, right? For example, if you have an enzyme is nothing else than a super large molecule that catalyzes a specific reaction. So these reactions are then to a certain degree a composition of lower level reactions, which might also be composition of even lower level reactions, right? So you play this whole level, and then you have, of course, these enzyme complexes that you see here, or sets of enzymes that then catalyze many reactions, and that's now we are very close to living species and what's happening in metabolic networks, right? So there's all these levels, right? And let me just show you 2 examples. For example, when you want to understand what one specific enzyme is doing. I mean, enzymes are extremely fascinating species, in my opinion, because they are highly specialized, large molecules. They are very specific. A specific small molecule goes in there, right? So that's what is illustrated here. And then you make the reaction that you want to do, and this is done via several steps, as you can see here. And then the enzyme is back in the state it has been, and you don't have any waste, right? So you have a waste-free chemical reaction sequence catalyzed by an enzyme, right? This is completely fascinating because I mean, it's very difficult to do things like that in a wet lab, that you have a yield of 99% or for producing something from a very specific ETAC to a very specific product. So here you see a very well-known enzymatic reaction, the beta-lactamase. So the enzyme is called the beta-lactamase, and also the mechanism is called beta-lactamase. Here, maybe zoom in here. Oops, that was wrong. So maybe I zoom in here. So here you see the EDAC molecule, right, which is the so-called beta-lactam, and very interesting, here's this 4-ring. And here you see amino acids hanging around. I mean, if you think about what a protein does, it has amino acids sticking into an active site, and you usually have something like 3 to 6 amino acids sticking to that active site, and there the thing is happening, right? And here, what is really happening in this specific reaction is that this 4-ring is broken, right? So the 4-ring of this beta-lactam is broken, right? And you get another molecule out. So you have a sequence of steps, right? And now you can, of course, take this sequence of steps and model them, you guess how, as graph transformation rules. Here you have exactly that sequence of 5 steps, right? So step 1, step 2, and so on. And here you see our modeling of the specific step of the beta-lactamase. You might already sense, so the specific modeling of this rule, this is where the art comes in, right? What do you put in the context there? But this is just to illustrate how we in principle work here. Here you literally see the code of our framework. You take those 4 or 5 reaction steps, you compose them literally on with each other, and you get the overall reaction of the beta-lactamase as a rule. You might get even many rules, because the composition might not just end up in one overall rule. But that's things you can do, and we illustrated this for the beta-lactamase. And since just 2 months ago, a project started together with Walter Fontana, the Harvard Medical School, and Christoph Lamm at the Theoretical Chemistry Group in Vienna. And we were lucky enough to be able to hire 3 postdocs, Juraj, Christoph, and Nikolai here. And they are exactly trying to come up with a completely new idea to design new enzymatic mechanisms by formalizing all known enzymatic individual steps and trying to expand then the chemical spaces that you can expand, and try to infer new mechanisms, which might hopefully eventually lead to new enzymatic designs, right? And already within their 2.5 months, so hopefully there's more to present soon, but already within just some months, they were able to actually formalize the database of hundreds and hundreds of enzymatic reactions, where you have also the individual reaction steps, translate them into graph transformation rules, expand chemical spaces, and they are currently up to, you should think really about it as Petri net markings. That's the current approach that they are following, and where you go from one marking to another marking via applying a graph transformation rule, and they are currently analyzing really spaces of several hundred thousands of nodes in order to find new mechanisms, right? So that was one example on the level of just one enzyme, right? And trying to design new enzymes eventually. Another one is on a more higher level, where you try to do enzymatic design, that's sometimes referred to metabolic engineering, when you try to use several enzymes to to combine those to find a new mechanism, right? A very famous example that we analyzed is the so-called non-oxidative glycolysis pathway, where, very briefly explained, if you eat a sugar molecule which has 6 carbons, right, this goes somewhere in here, then you basically create energy, right? And that energy is stored in so-called ADSCO-R molecules or pyruvates, right? But in this process, you lose carbons via carbon dioxide, right? So what these guys presented in a 2003 Nature article is, can we engineer something that doesn't lose these carbons? And they literally engineered it, right, on paper. And in the Nature article, you find 3 designs, right? And here on the right-hand side, you literally see a sketch of their design. Most importantly is this green box, where you basically see that the inflowing sugar molecule, which has the 6 carbons, produces not only 2 equivalents of this ADSCO-R, but 3 equivalents of this ADSCO-R, and the ADSCO-R has 2 carbons. Therefore, all 6 carbons are used, right? And that's what they engineered. Well, nothing easier than that. We just took the rules from the enzymes and expanded the chemical space, and we specified the problem that we want to solve, namely you get 1 sugar molecule and we don't want to lose any carbons via carbon dioxide. Find me a design, right? And literally we could enumerate many designs, including the designs that were suggested in the Nature article, right? And just to let you know where the technology here is, they really implemented their designs in vitro first and had a very high yield, so it works, right? And the goal is then to take such designs, change the genetic material of bacteria such that these bacteria then create the required proteins, and you have bacteria that implement that. And they also, I think it was not with such high yield, but they had a signal that this also works. So that is just another example of metabolic engineering. But what I want to use the rest of the presentation for is to more illustrate how we do this, how we exploit the fact that our atoms have identity, and we can trace the atom through large chemical reaction networks. That's work together done mainly based on Nikolai Norgaard's PhD thesis. Here as a motivation, something that people like Eric Smith also are analyzing a lot is kind of analyzing the metabolic setup of different species, also to bring them together in kind of phylogenetic sense, and also yeah. So this is one motivation. The other is, of course, to support such investigations, and the other is, of course, that the engineering technology is just out there, right? That you can specifically label an individual atom. And then, I mean, you just put an additional proton in the nucleus, and then you can let that labeled molecule run through a sequence of reactions, and then you get literally as an output from the bacteria a compound that you then can analyze with technologies like MS or NMR, which NMR can elucidate more the structure, and with mass spec you can literally measure the weight of the molecule, and then you can fragment it, and you can then have the weight of the fragments, and by that also find structure elucidation. But so what you see here already illustrated is kind of these dotted edges here, which illustrate where the individual atoms in the sequence of reaction goes. What you see here is the very famous citric acid cycle, right? So now will you come back later to this? This is exactly the example that Jakob also used on earlier slides from the Formose chemistry. Now, just to make clear how we use actually semi-group or monoids to more systematically analyze these atom traces. So here, just for illustration reasons, I have a very simple reaction where you have this glycolaldehyde molecule, which via a very easy isomerization reaction gets this molecule, and then this and this molecule can react together to this molecule. It's just two very simple steps, right? So now, if you take the morphisms from when you apply the graph transformation, right? You can, let's start with, we give all atoms in the complete network IDs, right? And let's give them ID I to N, right? And note, usually we we don't work with static networks, but intentionally we try to expand the networks in systematic ways, and then so we don't start from a static network. However, here I also start from a static network here with a network of just 3 molecules, and I label all atoms. And now I need to correct myself, because here, for simplicity of the example, I only label the carbon atoms. So then you can actually write down transformations in a semi-group sense, and what the transformation does to the identity permutation, right? So for example, if you have here 1, 2, 3, 4, 5, 6, 7, 8, then this specific morphism here, which comes from a graph transformation application, can be written down like that, right? 1 is mapped to 3, 2 is mapped to 4, and the rest is untouched, right? Well, you can also find another morphism here, right, which leads you to another transformation here. Then you have also the transformation that comes from merging 2 molecules, and there's also 2 ways of doing this, right? So you have these 4 transformations. With this, you can then build a Cayley graph, right? You start basically with this identity, and you just apply these transformations again and again, and you get this graph structure out, which is kind of showing you the fate of individual atoms via subsequent application of graph transformation rules, right? This, of course, would explode in large networks. Therefore, also, because you usually have a network, and then you say, well, I'm interested in my starting compound in these 3 carbon atoms, for example. So therefore, well, you can just make a projection of this Cayley graph, right? Where you just say, well, I'm only interested in the atoms 1, 2, and the atoms 1, 2 is the atoms of the original glycolaldehyde. This will lead to the fact that certain vertices will now be merged into one node, right, into this node, and it will become simpler, right? But you get this structure out here, and it tells you, so to say, the fate of the atoms 1, 2 that can happen through a sequence of all the reactions that we're modeling. Already that you can use now, for example, to kind of analyze chemical systems like the one that I show here, which is a very famous one, which is the so-called unrock mechanism, where you have this ring structure here with a bromine attached, and the bromine should be replaced by the so-called amide group. And you might think, because this part and this part is basically isomorphic, so you might think the bromine is just replaced by this amine group, but that's not the case. What is happening, what is really happening, the whole thing swims in ammonia, and that ring is actually opened up, and these 2 nitrogens are not these 2 nitrogens. So if you want to verify this, you must make an isotope labeling experiment, label the 2 nitrogens and follow them through the sequence of reactions. And of course, if you have pathway alternatives and you want to differentiate, is this one true or this one true, you need a hypothesis generator. So if you model it with graph transformation rules and use this Cayley projected Cayley graph thing, then you would see, well, in the correct mechanism, the 2, 3 here would be mapped to 14, 15, and in the wrong mechanism, it would be mapped to 13 and 14. I think I said it correctly. Yes, exactly. So you can use this as a hypothesis generator and eventually as a labeling design generator for the wet lab, really. So let's make this a bit more complicated, because this is, of course, a very simple system. So let's assume we suddenly now have rings, right? So let's assume we can go backward and forward here. Now you suddenly have the possibilities that you have an atom with 2 carbons, and then, well, certain sequence of reactions happening. You get the same molecule again, and you might ask yourself, are the same carbons in there, or did they switch position or something? That's what you literally see here. I will show this in a second in the TCA cycle. It should be more illustrative. But this block here now should basically say this comes from a strongly connected component, meaning, well, the atoms that are located at position 1 and 2 can flip their position to position 2 and 1. And here you see that's relatively easy. You go backward, you go forward and backward, right? But we call this a natural subsystem, basically motivated from Krohn-Rhodes theory and what Ekri and Nehani has been doing. They did this on other biological systems. Let me phrase it like that. They also use semi-group theory to analyze such systems. We apply it to chemistry, so it's related but not the same. But let me just show, to make the point of that, again, illustrate this in the TCA cycle. So you have the TCA cycle, right? So in a sequence of reaction, you come from this oxaloacetate compound, which is illustrated here and has the carbons I label here with 4, 5, 6, 7. You can now apply reactions over and over again, right? And here you see exactly in this graph here, which is the Cayley graph, right? The projected Cayley graph, actually, because we only we don't look at all the atoms, but only at the atoms 4, 5, 6, 7. But you see what can happen to these four atoms. And then you see here in color, actually, for example, the yellow one, that there are strongly connected components. Strongly connected components means you have a certain configuration that you can, via running in a cycle, meet again, right? This is what the gray boxes here are. So for example, this means you can have 3 carbons at position 5, 6, and 7, then you can run around in the TCA cycle and have exactly the same 3 carbons again. So this underscore means that specific carbon you cannot keep that one, so to say, but the other 3 you can keep. Or this also means you can have 2 carbons at position 5, 6, and you can switch backward and forward between. So you can alternate them in a backward and forward manner. And of course, people like Eric, who is also listening, would immediately say, no, that's not possible. That's not true. And he's absolutely right. That's not true in the real TCA cycle. And that's the point what I wanted to make. If you model this on a graph theoretical level only, then this would, of course, be true. But chemistry is more complicated, right? And some of these reactions, actually in this area here, are stereospecific. So you cannot model them just with the graph structure itself. You must include a stereospecific reaction. And it's actually that you cannot create all citrates, but you can only create this cis acetate and not this one, I think. So anyway, one of the reactions, basically one of the morphisms is killed, right? That's how I need to speak to a community like you with that. And if you do this, then you see that this projected Cayley graph looks like that. And this structure that illustrates the fate of these possible molecules from the oxaloacetate gets much more simple, and you have only one strongly connected component, meaning the only possibility to run around the TCA cycle once completely and keep a carbon is that you keep this specific carbon 5, right? I think I skipped that part. And because I also want at least to show 1 or 2 minutes presentation of Merkle. Maybe I first show the presentation. I know maybe I first make the conclusion, then I only need to switch one. So we use graph transformation and the techniques underlying there as one of several integral parts to model bio or biochemical systems. We actually also look at non-biochemical system connecting to pi calculus or whatever, or I mean, if it's funny, then we do it. But just to let you know that the complete machinery uses many more techniques than just graph transformation. I mean, we analyze, for example, when we expand these large chemical spaces and then try to find motifs, what we do there is a generalization of hyperflows, of flows, and namely integer hyperflows. So we use techniques from classical flow finding algorithms there, or ILP techniques there. When you try to find a synthesis plan that is somehow embedded in this large chemical space, we use algorithms for k-shortest path finding on hypergraphs. In order to analyze such pathways, we actually do a subsequent analysis with Petri nets. Graph canonicalization is heavily used. Of course, we also connect to chemophysical properties. This is where we get in connection to the quantum chemists, right? We also approach the whole expansion of chemical net. These chemical spaces sometimes get too large, so you need to sample. So therefore, we also do classical Gillespie simulations via stochastic simulations. Let me just, for the sake of also connecting more to the community that is listening here right now, maybe just to, not leave meeting, share, I want to do. share, right? Just to show you a bit of Merkle, right? And to connect to the presentation right now. What I want to do now is I want just to take an Aldol addition, and you can literally look at the Aldol reaction like that, right? You have left-hand side, the context, and the right-hand side. And literally the code to combine is actually here, right? So to compose two rules, you literally write it like that, right? You just say Aldol addition composed, and you see here, I use the most common combination operation, composition operator, which is of course leading also to non-chemical results due to the things that Jakob showed you, right? But nevertheless, I just want to show you that if you use this most generic one and you compose, let me just do this, compose, right? Then, and I just print one good rule here, right? And then I also print here one non-chemical rule. So here's the rule printing of the good rule, and here the rule printing of a non-chemical one. So if you look at that, then you see this looks exactly like that. So here's the original rule, right? And now I just compose this rule with itself. And then you get, for example, this overall rule, which is a chemically good rule, and I show you how I defined good, because you actually implemented this valence constraints that Jakob has presenting. But if you also allow non-good rules, so to say, then you get all kind of chemical nonsense here. Actually, is this chemical nonsense?
I think that's
well,
it's the next one that's the nonsense rule, I think.
Yeah, I didn't print no, actually, oh, I killed the, oh, maybe I should, okay, I wanted to have a rule here, maybe I should print two of them. Or maybe I just continue. Sorry, you, maybe to, now, of course, this is Murphy, right? So usually you would also now see a rule that is non-chemical, for example, having a hydrogen with two neighbors or something, right? But I just want to for the sake of this community, also show that you can now, of course, just compose rules with themselves over and over again, right? That's literally the code for that. And here I just compose rules over and over again in that sequence, and then I filter for, I only want to see the chemical rules, right? And above in the code, actually here, you see, usually you don't have to do this, right? I just want to make the point of it that you can do it. Here I just have certain constraints where I check rules with respect to the valence. For example, I just say I reject all the rules that do not fulfill my constraints that I now define, right? But if I then would do this and run this again, compose, and you see here already that you get a lot of rules, and I specifically chose a nice example where the rule composition leads to a lot of overall rules, but actually only exactly one of the overall rules is a chemical rule. And you just for the illustration of that, here you see now the rule composed with itself twice, the rule composed with itself 3 times, or 3 times in sequence, and here 4 times in sequence. So you see the pattern. Right, that is actually basically it from my side.
Yeah, maybe just a small comment, because now you saw Daniel playing around with this. So if you go to this URL I had in the beginning to mod.ematter.stu.dk, let me just write it in the chat. But then we have a live server where we have an instance running, and then you can interact with it, write Python code, and try it out. Yeah, maybe Daniel can briefly find it. Right.
Oh, I'm not online in my virtual box here, so I would have to share again.
I think.
It's cheminf. No, there's an F missing. Yeah.
But well.
Then I am online, yes, okay. Right. And there's software, Logicon, here you have the live playground, where you can play around with all kinds of examples here. Right. So you literally can run it, and you press then the, so a PDF file is generated for you.
Ooh, yeah, and I had to restart the server just before the talk. I think there's something.
That's Murphy.
Yeah,
let's stop
right.
that here. I didn't see this year. That's the first time.
No, the server was just restarted. So yeah, good. I'll get it fixed soon.
Don't worry. All right. Well, thank you very much, both to Daniel and Jakob. So let me clap for you on behalf of everyone. So yeah, so I suggest now that we sort of just open this up for discussion. So if you want to sort of unmute yourself, start your video if you like, then we can just have a normal discussion. I think there's about 23 of us, so we should be able to do that. My internet was just gone. Did you get what I just said? So I just said we can now unmute ourselves and just have an open discussion here. Maybe while people are doing that, of course, you can continue asking questions in the chat if you want to type. I mean, when you were talking, Daniel, it just reminded me that I was, I think I was giving my inaugural talk at the faculty in Leicester, sort of more than 10 years ago. And there were obviously people in chemistry and physics and so on. And so I thought doing a bit of chemical graph rewriting is a good way of explaining graphs and graph rewriting. So it's essentially using examples like you had in the sort of informal way and explaining in which sense these are graphs and so on. And then I think I also mentioned something that there is something specific about graph rewriting because you can track the identity of nodes from one step to the next, and you can basically use that in order to track atoms, at least in principle. I mean, just from a theoretical point of view. And then some of the physicists complained and said that from their point of view, sort of philosophically speaking, atoms don't have an identity and I shouldn't do that. If you come across concerns, I mean, I feel slightly vindicated by you because obviously you know what you're doing, whereas I was just sort of speculating. But have you come across complaints like that or observations?
No,
like that?
Not on the atom identity. So I mean, we work with quantum chemists quite heavily. Atoms have identity, period. So I mean, there is, you know, for them, for example, edges don't really exist. So, or at least the model of you have a single bond, a double bond, a triple bond, an aromatic bond. It's a continuum, more or less, right? So it's basically, I mean, a bond in this molecular drawing is literally a pair of electrons, an abstraction for a pair of electrons. So two bonds are two pairs of electrons, right? But specifically, if you come to stereochemistry or to more complicated setup, it's getting much more complicated. They're literally in their formats. They don't even model the bonds. For them, they just say we have atoms with positions. Bonds are inferred. So they literally have the densities of electrons, right? So there you need to be damn careful because you need much more flexibility with modeling the bonds, which we have to a certain degree, because in our framework we just say, well, you have a connection, you label it with whatever you want, right? So
maybe we're the wrong kind of physicists in our case.
No, it's Daniel and Reiko. May I jump in here, please?
Because
I think we can make some of the physicists be quiet by using other physicists.
That's
of course,
good.
Yes, a quantum mechanical object in a cold, clean vacuum is exchangeable with other quantum mechanical objects in that cold, clean vacuum. So you have symmetry rules and you have superposition. But a classical atom has an identity, and the thing that makes a quantum atom into a classical atom is decoherence. And so many of the nuclear centers that you have in a large molecule are coupled to the solvent. They're coupled through vibrations in the molecule to very non-local structures. And it's the fact that they can become classical that allows you to track their identities reliably. So then there's only a small subset of the quantum particles that are sufficiently isolated or sufficiently delocalized that then it becomes important to recognize their extended quantum character and superposability. So things like the spin pairing correlations in aromatic sets of bonds are of that character. So even something so simple as a proton, which you would think is the most quantum mechanical of things, most of the time it behaves like a classical object. And there are only a few cases when it's actually productive to treat the proton as a quantum mechanical object capable of tunneling or superposing with other protons in hydrogen bonds and things like that. So there is a kind of a nice way to talk about which regime you're closer to. And that, you know, through 10 million years of applications, the chemists have sort of settled on rules of thumb that they mostly trust.
Yeah, thanks a lot, Eric. I mean, I think this is also, you know, I mean, Eric is a physicist and we collaborated with him heavily, or still do, as we find time. Jakob has been working with him directly at LC at Tokyo Tech for whole 2 years it was, right?
Yeah, 2 years.
Yeah. And I mean, you might sense it if you're from the craft transformation community, you need to be able to speak other languages. Right. So, and it's very important, right? And people like Eric are just wonderful because they are the Babelfish for researchers, in my opinion. So they translate. So that's wonderful.
May I ask you another question, though, please, if others don't want to come in the queue, that I put in the chat very much at the beginning?
Oh, yeah.
It has to do with your basic, the tokens in the underlying abstraction. It was in Jakob's presentation at the very beginning where he talks about the fact that an atom can have types. It can carry a charge or not carry a charge or something like that. And I wondered whether you have considered the following alternative abstraction. If we ask what is the most basic abstraction in chemistry, you could say that there is anti-symmetrized spin-paired electrons, which define the pairing operation. And then there's how many atomic centers might be sharing those electrons. So things like atomic charge would then be derived from a property of what spin-paired electrons you have and how many atomic centers share them. So you could imagine an alternative fundamental abstraction for Merkle, where essentially what you keep track of are paired or unpaired electrons, and then how many atomic centers share them. So now there's no such thing as an ionized nitrogen or a nitrogen with a non-bonding pair. You could introduce a new type of atom, which is the null object. And then a nitrogen with a non-bonding pair has a spin-paired state shared between the nitrogen and a null object. And, you know, a metal, the different states of an iron could have the same overall charge, but it could have 3 unpaired electrons, or it could have 2 paired and an unpaired. And then again, by introducing a rule system where you can replace real atomic centers with a null object, you can look at when occupied and unoccupied orbitals can create a bonding pair. You could, by assigning electronegativities to atoms, you could say that when a bonding pair is shared between 2 centers, you could compute the fractional charge and the degree of covalent or ionic. So always you have an abstract language where you want to choose the basic abstractions so they express what you think is the chemical reality in the underlying system, compact, so that you have a low-level abstraction. I know you guys spent years in choosing the basic foundations of Merkle. I wonder which of these things you considered in the course of that development.
So there's a lot of trade-offs here, and in principle I agree with you that this is a more fundamental model because it goes back, well, it goes close to the physics of it, and in some sense the stereochemistry extension also introduces lone pairs, lone electron pairs, and really you are right, then exactly charge is something that we can infer if we have all the other information. But I think that the trade-off here is that one thing is that this work on chemical gas transformation actually started in Vienna, even earlier, before I began to work on it as well. But there's a trade-off between having a model which is fundamental and then having a model in the sense of it's directly usable for non-physicists, if I may be so direct in it, that the nice thing about the current model is that yes, it has these icky corners, but it's directly one-to-one how I imagine a introductory chemistry lecture might describe molecules. A second thing is also how such a model will translate into the algorithms. Because we definitely want things to be fast. It's just, well, whatever we can get of optimizations will just make our compute even larger spaces. So there's a careful trade-off between not introducing things into the model that might make it more fundamental, but will be very difficult to implement in optimally to, for example, enumerate morphisms fast, do isomorphism check fast. So that's kind of the trade-off, and I think that the current model is a nice trade-off in that respect, but definitely if you want to go to exactly having the correct stereochemistry, at some point when we venture into metal chemistry, definitely there needs to be some more careful thinking of how do we actually represent this and make rules that make sense in that space.
If I may augment from the perspective of what we have and where we went in that direction, basically based on discussions with exactly the quantum chemists, right? Because when it started from how does the data look like, and then you realize, well, they don't model edges. And then actually, when you speak with them about double bond and single bond in molecules, then they say, yeah, well, but it could also be the other way around. Basically, it's a superposition of everything. So there we already went into the direction of using the first order terms and basically saying things like, you are a carbon and you have 3 neighbors, which gives you then flexibility in the way how, I mean, you don't specify you are the bond with a 2 electron pairs. So that is, and the first order terms allow you at least to go in that direction. And I think that at least the first tests show that that works reasonably well. So the classical molecular modeling maps good into that modeling, which is of course still far from what you have been suggesting, Eric, but I mean, at least it's in that direction. So.
Okay. I think Lean had a question about application conditions. So Lean, do you want to ask that yourself?
Yeah, I can. I was just curious. Maybe I missed the example or the motivation because I was a bit late for your talk, but I would just be curious where application conditions would come into play in your application field, why you need them and how you need them, so to say.
Yeah, so one thing is there's of course the fact that it would be fun to have just for the sake of having them and playing around with them. But besides the fun of it, there are, and I didn't mention the specific example of where this is relevant, but we already have a need for doing certain kind of degree constraints, counting number of degrees and restricting that. And yes, we have a constraint system for that. It's very basic, but it's pragmatically it works. But we're also seeing that there are cases where suddenly, exactly also Eric mentioned a bit about prebiotic chemistry. You ask a chemist, okay, what reactions can happen, and they draw something on that piece of paper, and they say, actually, well, there's this R group, but this R could be either this one or this one or this one, and each one of these selections could then say, well, actually, this one can further be specialized into these 5 different ones. So in that case, of course, it can be expensive to have application conditions. In the end, it might be better to duplicate rules with different contexts. But just from an expressiveness point of view and just as a modeling, just prototyping a model, it would be very nice to be able to express this in a very concise way. And it would open up a new way of modeling reactions that we don't have available at the moment.
Also, to augment here, so that when we model chemical systems, I mean, we can, if we can put information into the rules, like constraints that are nicely where the chemists agree, that is the best, specifically as we are then able to compose the rules even when they have conditions. But often the way this can also become more complicated. For example, if it's suddenly like thermodynamics, the Gibbs free energy of a compound must be decreasing while applying a reaction. So we basically have then callbacks. So you apply a graph transformation and you get the double pushout diagram essentially back, and then you can handle this as an object and then write a function that accepts or rejects what you just did with whatever tool you want. So that's a very typical thing that we do. So, and it's a trade-off sometimes. So do we put it in the rule, or do we do this? Sometimes we cannot put it in the rule, like the thermodynamic conditions. At least I don't see an obvious way there.
Yeah, but as I understand, you would also need these kind of graphical application conditions. So really, no.
Yeah, I think that would be nice. It would be a nice extension instead of looking at specific examples. Say, well, actually now here we invent a very dedicated constraint that is not part of the normal formalism.
Yeah.
As I said in the beginning, we're kind of in the middle. That's kind of if somebody invented a formalism that we can bend a bit and then use, that would be nice instead of inventing our own thing. So as application condition exists in the graphical sense, why not just stand on the shoulders of giants?
Yeah, and software engineering, this has worked out already quite nice, I would say.
Yeah, exactly.
So actually, if I may maybe quickly comment, so because I know a little bit also the work of Len and of Fernando and I think other colleagues, because there's this beautiful technology of Tableau-based reasoning, and especially the type of constraints you have in chemistry are quite intricate actually, because you have these valency constraints, but the valency can be realized in many different connection patterns, so to speak. And as an observer, maybe have a feeling that this Tableau-based reasoning might be quite useful to have a look at in chemistry. But I mean, again, I'm just commenting. Maybe Lynn, you can.
Yeah, what we do there is actually automated reasoning for graph conditions. No? So when you have a graphical condition, so to say, you can wonder if this is satisfiable at all, or if there exist any graphs that would satisfy the property expressed in the condition. And then we have automated reasoning mechanisms to give you the answer to that. On the other hand, we use these conditions also as application conditions directly attached to a rule. And there you can then use them to express that something doesn't exist before you apply the rule. I didn't hear an example like that yet, but this is actually the most popular kind of use of these application conditions in software engineering, I would say, when you apply graph transformation there. But you can also go beyond that. Heiko wants to add something.
There was an example in Jakob's part, I think, where it's essentially showing an implicit application condition saying that you can only add an edge here if there isn't already one, because the graph model doesn't support or you don't want, let's say, parallel edges.
Exactly.
So I mean, that's a very typical example where these negative conditions come from. In other cases as well. So there are certain structures that you don't want to generate, and because you know that they don't exist in reality. So you have kind of conditions specifying the constraints. So these are the general graph constraints in a sense. They apply to all graphs that you can generate. And then you can turn them into application conditions that prevent rules from being applied exactly if they would generate something that is forbidden. Yeah, so that's a nice connection between these graph constraints that represent global restrictions essentially, and the local restrictions that you put on the rules in order to not violate the global restrictions. Yeah, and the Tableau method sort of I mean, it's not as straightforward as that, because sometimes you have constraints that need sort of combining with other constraints and so on in order to prove that is the case. And that's why you need these Tableau methods. So you basically need logic in order to reason about these things.
Right.
Yeah, but it's quite so I think the interesting case here is not so much that this is very good in terms of runtime, but maybe that you can sort of formally verify that certain bad things will not happen, for example, if you have a certain set of rules under certain conditions, and then you don't need to check for this at runtime.
Yeah.
That would be my instinct anyway.
Yeah.
It's when you extract rules from reactions, so to say, as I saw in your talk, no, then you can express the positive changes, so to say, so the context that has to be there in order to have the reaction. But maybe there is also some negative thing hidden there, no, that you shouldn't have some structure in order to have the reaction. Maybe this is something that needs to be expressed as well, and it makes your simulations more precise then.
So I want to understand at runtime from Raiko. So are you saying by that you have a set of rules that are not applied yet, and just by looking at the rules you infer that certain situations cannot appear or appear, right? Okay. And that's of course that's extremely interesting from a chemical point of view, right? Because you basically, if you analyze only the rule set without that our approach is usually that we expand spaces, right? And then we either make stochastic simulations, and then we put all kind of machinery on top of these spaces. And I think that's also valid. But of course, it's much more elegant if you would find out properties based on the rules only, right? I mean, I can also understand. So Nicolas is probably, I see the bubble saying tracelets there.
Exactly.
Quietly in the background, yes. Sorry.
It's essentially the distinction between static and dynamic analysis. I would call that in the software analysis world. Yeah, but you're right. So it's. I mean, I think what you buy, what you pay for it, is that you have a slightly more complicated formalism, which has. I mean, composing rules with application conditions, for example, is more complicated, and so. But yeah, on the other hand, the rules basically carry their own conditions with them that you don't have to express as global conditions. Yeah, so it's a way to localize these things.
Yeah, it's definitely an interesting direction of taking this and exploring what can come out of it, because well, if we can certainly begin to do a new type of analysis of these rule sets, there might be some chemical connection where this is really fitting. So yeah.
I mean,
should maybe advertise that Len and Fernando will give a talk here in the series. I think on January 29. Is that corrected? Yeah. So to be.
I guess so. Although it will be on something a bit different, but we will also mention application conditions there. Yeah, it will be on Confluence, but maybe it's also interesting for chemistry. Who knows?
Sorry, Daniel. I just wanted to mention this quickly.
Yeah, sure. Confluence is another. I mean, there is a definition of confluence in chemistry. I fear that's not the confluence that you mean. Yeah, I don't know. Yeah, what did I want to say? I actually. I mean, I didn't find too many, but maybe this is really lack of being deep into your community. Not too many results on generic whatever when you learn about context-free grammars or context-sensitive grammars, and then you just by looking at the rules you can then infer certain things, right? On a graph transformation level, I didn't find many results where I kind of say, oh, that's clean and we can use it, but maybe this is just my lack of my ignorance or being able to pass the formalisms. I don't know.
I think it's I think if you look at it from a formal language point of view, of course, I mean, Mark is much better at this than I am. So if he wants to comment, but I think, I mean, the hierarchy is not nearly as interesting, I think, in the sense that regular grammars hardly make any sense. Anything beyond context-free, is hopeless. So the only really interesting subclass are essentially context-free languages and sort of minor generalizations of that in terms of formal language theory, for example. Similarly, relations between graph languages and automata are much more complicated. So So you don't have that neat link between, like in string languages, between regular languages and finite automata, for example, or context-free languages and push-down automata, because the notion of graph automata is not as canonical. I mean, Barbara has done some work, Barbara König has done some work on that, trying to understand what that means. What are push-down automata for context-free graph languages or things like that. But it's much more complicated, so it's not as obvious in a sense. And you basically spend a lot of time getting the definitions right, whereas in other cases the definitions are quite clear, and then the meat is in the connections. But so that's the formal language theory. But if you go to the concurrency theory, so I mean confluence and things like that, sort of independence, or if you go to so concurrency theory, I would see sort of in the tradition of Petri nets, if you like, or if you go into maybe sort of logic inspired aspects, I think that becomes much richer, because a graph is a relatively natural interpretation of a logical structure, as you're aware. So relational structures, in a sense, are very close to graphs, or are graphs, if you want to be a bit sort of flexible with the notion of graphs. And then the connections of that with graph constraints, with negative application conditions, and so on. I think that is an area where things are quite natural, I find. And where you also get sort of meaningful results, or results that you can understand at a relatively high level without sort of having to sort of engineer the definitions too much. Yeah. Okay, so I don't know. Anyone else has any questions, any comments, anything they want to say? Have we covered the interesting questions from the chat? I mean, you had a chance.
So maybe just quickly. So if nobody objects, I would just quickly stop the live stream, but we could still stay and discuss for a little bit. It's just because of the, what we put out to YouTube. So especially if somebody has some some very insightful, probably industrially interesting ideas, we could discuss them now in private. So I mean, we could stay here. I'm fine to leave the stream open, but I would maybe just end the live stream if that's okay.
Yeah.
Reiko, do you want to say a final word to the live stream?
Thanks for joining, and see you in 2 weeks.